Okay, so we have started recording already. We're gonna do this last chapter for this break over here, this June holiday. So we're gonna do on this final chapter. This is actually quite a small chapter on ammonia. So this one, if you realize you see your textbook, there's only very few pages only. What are the few things you'll learn? You'll learn how ammonia can be made, okay, and also what are some of the reversible reactions. Actually, the key thing here, obviously, in this chapter is this one. It used to be a lot more materials inside, but in the new revised materials, they use ammonia just to introduce reversible reaction and also how is it made industrially now. Okay. Uh, okay, so let's carry on with this. Okay, so let's start from 10.1. So in 10.1, what we're going to cover is to describe the manufacturing, okay, or describe how ammonia is being manufactured. Okay, so this one is really like looking at the industrial process. That's what we're going to cover later. And what are the raw materials that we're going to be using to prepare ammonia is actually nitrogen and hydrogen. So these are the reactants, or I should say the raw materials that we use to make ammonia. Now, the interesting thing is we need to interpret data relating to the conditions, okay, used in industry for processes. Now, the whole idea is that later on we'll cover some of the ideas, how the conditions actually helps the industry, okay, to manage costs, but also to increase what we call yield. The idea of yield, so I just want to write this down. Yield is actually the amount of products formed. Okay, so the higher the yield, then actually the better the higher the yield, the better the industrial process is. Okay, so in actual fact, when you look at production, they will always look at these two parts, which is first thing is about the speed. The faster I can produce means I can earn more money because there are more quantity produced, right? Okay, the yield is that for the amount of materials I put in, how much of the products actually is coming out. So we'll cover these two parts later. Okay, so let's start on this. Why we focus on ammonia? Okay, because ammonia is actually the most commonly produced industrial chemical, right? One of the most produced common industrial chemicals. Okay, about 80% is used to making fertilizers because fertilizers actually contains nitrogen, and you realize ammonia itself contains nitrogen itself. Okay, they can also be used to manufacture plastics, explosives. TNT is actually one of those. One of those explosives that contains a lot of nitrogen. Okay, textile, pesticides, and other things. It can also be used in cleaning materials. Now, so these are just the general idea of why ammonia is being studied because it's really one of the most commonly produced industrial chemicals. Okay, so let's start now. How is ammonia manufactured? It is actually by this process called the Haber process. So you will see this term regularly, the Haber process. So Haber process is the process that is used to manufacture ammonia. Okay, so what are the raw materials as mentioned at the top? The raw materials are actually nitrogen and hydrogen. Okay, and figure 10.2, which is over here, okay, shows how these raw materials are obtained. So first thing is that nitrogen gas is actually obtained from the fractional distillation of liquid air. Can you please put a star here? Okay, because it is commonly asked how is nitrogen gas obtained in the Haber process. So what they do is they collect the air. After they collected the air, they let it undergo fractional distillation. Okay, and in the fraction, I can collect nitrogen. Okay, because the gases have different boiling points. Why are you able to do fractional distillation of liquid air? Because the gases have different boiling points. So this is a quick recap on your separation technique. Different boiling point. Okay. Now, with regard to hydrogen gas, okay, so hydrogen gas is actually obtained from the cracking. Okay, the idea of cracking is actually the breaking down of crude oil into fractions. So when you do this thing called cracking, okay, cracking is actually the breaking down of crude oils into fractions. So think of your crude oil as a big molecule, big molecule. So this is like your crude oil molecule. Okay. So when you do cracking, you're actually breaking it into pieces. And as you break it into pieces, okay, hydrogen gas will be produced along the way. So that's where they get the hydrogen gas for this Haber process. So pausing over here, general idea, N2 is obtained. How is N2 obtained? From fractional distillation of air. Okay, distillation. Now, to be more precise, actually, it's fractional distillation of liquid air. You must cool the air down first, okay, into a liquid, then you can do your fractional distillation. So I just want to take note, the word liquid is important, okay, and it's not distillation, it's fractional distillation. So a lot of students tend to miss out the word liquid, okay, they just put fractional distillation of air, it doesn't work. It needs to have the idea of liquid air inside. The other one, hydrogen, okay, is obtained from cracking of crude oil. So as of now, you're not very sure what exactly cracking is yet. You actually learn this only in Sec 4 lah. Okay, so just take note of this. So H2 is actually obtained from cracking of crude oil. So for now, just learn this first. You will be able to get to this particular part when you reach Sec 4 near the end. Okay, near the end, you'll pick this up in Sec 4. Okay, so Haber process itself, so I should say the reaction here is reversible. The reaction here refers to the production of ammonia from H2, which is hydrogen gas, and N2. So it is a reversible process. So what does it mean? So take note of the definition here. It is a reaction. They can go forward and backwards at the same time. So don't just say it can go forward and backward. You must say the forward and backwards at the same time. So it's happening concurrently. Yeah, okay, it's happening concurrently. So how this similar one reversible reaction that you tend to see is when you look at weak acids. So if I got ethanoic acid, you realize we write this reversible arrow to give you CH3COO minus plus H plus. So this arrow here represents reversible reaction. Okay. Now, so how would we represent it? Okay, you can see from this equation over here. So the double arrow is used to show the reversible reaction. Okay, from the left to the right, that means this direction. Okay, this direction. This is forward. Which means it is N2 plus H2 becomes NH3. Then what is the backwards? Is actually right to left. So this is backwards. So now take note, the backward reaction is this. Okay, look at the way how I'm writing. Okay, so I realize I never balanced the equation. Let me balance the equation. 2 here, 3 here. Okay, so you realize when I write backwards, the backward single arrow, I don't draw. Sorry, I just want to say, when you do the backward reaction, I didn't use the backward arrow. It is still a forward arrow because all chemical reactions use a forward arrow. Okay, but it's just that to show you that the reaction is reversed, you can see over here lah. Okay, so this is the Haber process in terms of where the raw materials are from, which is nitrogen and hydrogen. And the other concept is actually the idea of reversible reaction, okay, of having it forward and backward at the same time. Okay, so as you can see here, indicated here. Okay, so few things here. If nitrogen and hydrogen reacts very readily, then we'll always get ammonia gas produced. But in real life, it is not lah. Okay, in real life, it is not. Okay, so take note, at room temperature, my nitrogen gas is unreactive. N2 is unreactive. So at room temperature, it is not. Okay, so the forward reaction does not take place. What we need is a high pressure and a relatively high temperature is required to start the forward reaction. So I just want to take note, there's two conditions here: high pressure, high temperature, in order for the reaction between nitrogen and hydrogen to start. In this process here, they also use this thing called a catalyst. So iron itself is the catalyst used. Okay, iron is added as catalyst to speed up the reaction. So what catalyst does is to speed up the reaction. Those of you who does bio, okay, you realize that, yeah, I know what's catalyst. Okay, so catalyst actually help to speed up the reaction. So in actual fact, this Haber process here is not just about having the raw material 1, raw material 2. You still need to have high temperature. You need to have high pressure. And you also need to have catalyst. Okay, so this is what's happening industrially to produce ammonia. Can? Okay, now if all okay, can you just give a thumbs up? Okay, good. Okay, come, let's carry on. Okay. Next part, let's go on. Okay. Now, so we went through how the forward reaction can take place. I must give high temperature, high pressure, and catalyst. But the interesting thing is this: because the reaction is reversible, the ammonia that we want can actually break down and decompose back because it is a reversible reaction. Okay, because the reversible reaction, the ammonia can break down, so it can go to a backward reaction. Okay, therefore, the pressure and temperature have to be carefully controlled. So it's not just about having it a lot of a very high temperature, very high pressure, that's good, but they will actually manage the pressure and temperature. So think of this as industrially, of course, what I want is high temperature, high pressure with catalyst. But industrially, in real life, I will not do it. I'll manage it in terms of not super, super high temperature, super, super high pressure, because this will affect my costs. Okay, this will affect my cost. Now, how does it affect cost? Let me show you. Okay, so figure 10.3 shows the effect of pressure and temperature on the yield of ammonia. Okay, the yield is how much ammonia is produced. Okay, so if you look at this here, if you look at this, so ignore the various lines. Let's just focus on the 450 degrees Celsius line. You realize that this one here is the yield. This one here on the x-axis is the pressure. What you realize in terms of the line, okay, it is that as the pressure increase, okay, higher pressure will lead to a higher yield of ammonia. You can see here, when the pressure has increased gradually, okay, as you increase it, the yield of ammonia increases. Okay, so if I got higher yield, this actually leads to a faster reaction. Okay, this also leads to faster reaction. So higher pressure leads to higher yield plus a faster reaction. So this pressure has two effects. One is higher yield. That means I got more ammonia produced. Second one is because it will also cause the reaction to become faster. Now, and hence actually what I want to do is the higher the pressure, the better it is. Why do I want to not have higher pressure? Okay, so the key idea here is pressure comes at a cost. So maintaining high pressure, think of it as my equipment needs to be more expensive. I need a larger amount of electricity. So maintaining higher pressure incurs a larger cost, right, because of the expensive equipment and large amount of electricity. Therefore, pressure is compromised. That means I try to find a middle point such that it is good, but not excessive, so that I can manage the amount of money I need to spend. So therefore, instead of going for a 400 ATM, instead of going for 300 ATM, they were actually, industrially, they use 200 ATM for the pressure. Okay, this is to manage, this is to manage the pressure. Okay, this is to manage the pressure and the cost. Okay, so still got high yield, still have faster reaction, but maybe because of the higher pressure, but in terms of the yield, in terms of the amount of energy, I'm still trying to manage so that the cost will come down. Okay, okay. So that's in terms of the graph here. Just focusing on one line to focus on the pressure. You realize if I just focus on 500, if I just focus on this 500 line, it will also tell you the same thing. Where I increase the pressure, the U will increase. Same thing for 600 degrees Celsius. If I just focus on one of the line only, you realize that as pressure increase, the U increases. Okay. Now, next part, let's see how temperature affects the U. Okay, so you realize at lower temperature, it leads to a higher U. Why? 450 degrees Celsius. You see, wow, the U can go all the way up to maybe 41%. So good, eh? Okay, why is it so that the U is higher? Why is it that the U is higher? It's because it reduces the decomposition of ammonia, which is actually the backward reaction. Okay, there's a higher U because it reduces the backward reaction, which is the decomposition of ammonia. But the problem is, if my temperature is very low, okay, it will slow down the reaction. You know that at temperature increase, my reaction speed will also increase, right? So I need to balance both the speed of the reaction and also the U. So you realize it's always about speed and U. You realize I'm trying to balance the speed and U. So you realize high temperature will actually reduce the U, okay, but it will increase the speed of reaction. So you realize high temperature has one negative effect, one positive effect, whereas pressure has both positive effect. So just take note in terms of this Haber process. Okay, doesn't mean higher pressure, higher temperature is good. It really depends on the reaction. So in this case, you can see clear cut. Pressure increase both U and speed, but there's a third factor which is cost that comes in. Okay, but the cost also increase, which is not good. Temperature actually same. If I increase the temperature, obviously the cost will also increase because higher temperature means I must use more energy to maintain that high amount of heat. So therefore, people will tend to actually use lower temperature as much as they can, but not compromise on the speed of reaction. Okay, so in this kind of particular question, okay, in this kind of particular question, how will the teachers ask this kind of, in terms of this chapter? They'll always give you the graph. So they'll show you the graph. Then they will ask you to explain how speed of reaction or the U of reaction is affected by the temperature or the pressure. Either one of them. Okay? And in this explanation, generally, they always ask you to quote data. Whenever you see data in your code, or they say with reference to a graph, you literally, I say, you literally please go and do this. Okay, erase this line. I need you to do this. Do the dot 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 dot. Okay, then you can say, oh, here is 100, 100 ATM, 20%. Then we have 300 dot 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 dot. And this part here is 300 ATM, 41% U. So you can say as pressure increase, okay, then you put bracket, pressure increase from 100 ATM to 300 ATM. So you can see I'm quoting the data here. So I not just say pressure increase, the U increase. I said there's a pressure increase from 100 to 300, the U increases from 20% to 41%. So this is what they mean by explaining with data, or with reference to the graph, explain the graph trend, or explain how the yield of the reaction is affected. This is what they mean by it. So just take note, quoting of data is important. Okay, so I'm going to put U star here so that you know where to refer to. Okay? Okay. So we talk about how pressure affects the reaction, how temperature affects the reaction. And the last one is really about catalyst. So in general, the reaction is actually slow despite having the high temperature and pressure. So that's why they add a catalyst to speed up the reaction. Okay, they add a catalyst to speed up the reaction. So you can see here, it's very businessman kind of thing lah. Okay, the higher the temperature, the higher the pressure, the faster it gets, the more product it can get. Actually, the better it is. Okay, I want to reduce costs. I want to increase product, increase speed. So this in general, a very kind of like in real life business kind of sense, because those people who make this Haber process, this plant, industrial plant, they are not the real chemists. The real chemists are the ones at the back end. These people who make the plant just wants to make money. So they always tell the chemist, can you help me make it faster? Can you give me a higher yield? Can you help me earn more money? That's what they want. Okay, whereas the chemist, you're looking at from the chemical reaction point of view. Okay? So this chapter itself actually links up science quite nicely with business. Okay, with business where there's a cost factor involved. Okay, so at the end of the day, what is normally used industrially, okay, for the minimal cost, maximum yield, plus best speed. I cannot say maximum speed, I'll say best speed. So I want the maximum yield for the minimum cost. They actually go for pressure of 250, temperature of 450, and then they have the catalyst, the finely divided iron catalyst. Finely divided actually generally, it is sort of like powdered, but it's not powdered lah. Just think of it as like cut until very thin strips. In general, they're actually very thin strips. Okay, so finely divided iron as a catalyst. Can? So there are 3 conditions for Haber process. They will tend to test you on these conditions. So you just have to be taking note of it. Well, literally the numbers, the 250, the 450, and the finely divided iron catalyst, you need to know. Okay? Okay, thumbs up if all okay. Any questions so far? Thumbs up if you are okay. Okay, good. Let's carry on. Okay, now, so we are now going to look in terms of what happens in the plant itself. Okay, in the industrial plant itself. Now, let's look at this. Okay, I realized, did I balance my equation properly? Yeah, correct. Okay, oops. Okay, let's go back to here. So let's start from the first part here. You need to feed in your raw materials. So in this case, I got nitrogen and hydrogen gas mixed in 1 to 3. Why? Because nitrogen plus 3 hydrogen will give me 2 ammonia after you balance the whole equation. Okay, let me be more precise. I should use a reversible arrow here. So you can see it's a 1:3 reaction ratio. That's why the nitrogen and hydrogen are mixed in a ratio of 1:3 by volume. Okay, next, once the gas is pumped in, it will go here and it will get compressed to 250 atm. So like you see here, this is where I'm trying to make the condition happens. Okay, so I compress the gas such that they become at 250 atm. Okay, atm is atmospheric pressure. So it's 250 times of current atmospheric pressure. So they really squeeze it in. Now what's going to happen is after I compress it, I will now push it here and it will flow, go it down, and then it will move up. As it moves up, it will go past all the finely divided iron. So it will go flow over the catalyst. And this whole chamber here is also heated to 450 degrees Celsius. Okay? Now, after let it go through, take note, only 15% of the mixture leaving the chamber is ammonia. So out of 100% of the raw materials that I put in, actually the yield is only about 15%. It's kind of ridiculously low lah. Okay? But that's how it is. So industrially, if you can maximize, you can push this 15% to 90%, I tell you, you'll be a very famous scientist. You'll get IP rights already. Okay? With the IP rights, you can sell for big money already. But chances you need to study more lah about this whole thing here. Okay? Now, so 15% is ammonia. So only 15% is ammonia. I still got about 85% of nitrogen and hydrogen. Now, if I just let go of this hydrogen and nitrogen, it's actually a waste. Why? Because when this one is let go into the air, I'm losing 85% of the raw materials that I pumped it in. So what they did was actually very clever. This person who did this whole industrial process is because they know that I can actually cool the substance down. Okay, the whole mixture is cooled and condensed. Okay, it's cooled. Sorry, it's cooled. So it goes down here. It's getting cooled. Now, the interestingly, it will cool it down such that only the ammonia gas condenses. Only the ammonia gas condenses in the liquid. The hydrogen and nitrogen gas will not get cooled down sufficiently for it to condense. It will still remain as a gas and it will flow back out. Okay, so the liquid is now pumped into tanks and stored. So imagine there's a tank here. It's pumped to tank and stored. The unreacted nitrogen and hydrogen is actually pumped back into the converter. So you can see the whole thing comes out here and then you'll go through the whole process again. So you realize they recycle. The whole system is kept close so that the nitrogen and hydrogen do not escape. They will just keep collecting all the ammonia that is being produced here. So there's zero wastage. So you then, in this case here, I will actually maximize my cost. Maximize the cost savings. Or you cannot say maximize the cost. Everything become expensive. So there's actually zero wastage. There's maximum cost savings. Okay, so this is a very smart way of doing the Haber process. So if you do engineering, or I should say chemical engineering, or any type of engineering, it's really about creating a system that can maximize your profits, okay, or maximize your reaction. Okay, because in real life, you don't always get 100% most of the time. Okay, can? Okay, so this is inside the Haber process plant. You need to remember the steps. Most of the time you are not expected to draw. You just remember the steps of how it works. Think logically, it will help a lot. Okay, don't just like memorize the whole thing. Think logically, that will actually help you in terms of getting the flow of the whole thing. Okay, thumbs up if okay for me to move on. Okay, let's go. Okay, so actually, we are done with the Haber process already. Okay, that's the production of ammonia. These are some practice questions, which I think is quite good because they actually highlights the idea of the conditions that you need to know how to explain. Okay, so this one you can do as homework. You can send it to me when you're done. You just get me to check your answer. Okay? Okay, this is the last part here, which is what are some of the reversible reactions. Okay, so let's go. Now, so one of the reversible reactions actually is this copper 2 sulfate, the blue crystals that you tend to see in and in your labs, or the blue solutions, generally is copper 2 sulfate, but solution form. Okay, most of the time when you see the blue crystals, they actually contain this thing called water of crystallization. This is the water of crystallization. Okay, so they contain some water inside them. Okay, now, so when you heat it up, so these are the blue crystals. When you heat it up, all the water will be lost, and you actually get this white solid. The copper sulfate actually becomes white in color. Okay, but then if you add water back, it will actually revert back to your hydrated crystals. So you realize, oh, sure, you mean you mean your copper 2 sulfate can change color? Yeah, can change color with the water of crystallization. So this itself is a reversible reaction. Okay. Any questions so far for this one? Thumbs up if okay. Okay. Let's go next. Okay. I got actually these are some of the other reactions. So you got another one which is your ammonium chloride. So this is another reversible reaction. This one actually covered this in chapter 1. Okay, so you realize we have covered this in chapter 1. When you heat it up, it will actually turn to NH3 and HCl, but then it will recombine back to form NH4Cl. So this is another one of the reversible reaction. So take note of this one. Okay, or this whole reaction here. Okay, another reaction, this thing called the contact process is also reversible. It's actually from your SO2 reacting. So this sulfur dioxide, you readily react with O2. Okay, you can actually form SO3. And once SO3 is formed, you let it dissolve in water, it actually forms a sulfuric acid. So this production of sulfuric acid also involves itself a industrial process, okay? A reversible reaction. Now, this is the interesting here where you need to interpret the graph. So I can give you an industrial process graph that involves some sort of reaction and get you to interpret it based on what you learned from Haber process. So if you look at this particular question here, this is the reaction, okay, over here at different temperatures and pressure. So focus first thing, don't look at all the multiple lines, just look at one of the lines. So let's look at the 1 atm line, where the pressure is at 1 atm. So what you realize is that at this kind, first time, low temperature, at low temperature, higher U. Okay, so let me reframe. I should just go by the pattern. So let's split this up. So you realize this graph actually can split out into 3 parts. So when when temperature is below 400 degrees Celsius, what do you realize? The U is high at about 95% to 100%. To 100%. So how do I know? Because when I do this line over here, you realize this is about 95. Okay? So when it's below 400, or you can say 0 to 400, okay, the U is about 95 to 100%. Then between 400 to 800 degrees Celsius, okay, the U drops drastically or drops sharply, okay, from 95% to maybe this is about 15%. So you can see here the pattern is high U, below 400. From 400 to 800, there's a very sharp drop in the U from 95 to 15%. And the last part is from 800 degrees Celsius to 1000 degrees Celsius, the U decreases slightly from 15%. Actually, not. Okay, maybe not decreases slightly. Decreases less steeply from 15% to, let's take this as about 10%. Okay? So you can see how I look at the graph and then I describe it accordingly based on my knowledge of reversible reactions and also interpretation of the pressure and temperature and stuff. Right? Next one, I can think in terms of the pressure. So you realize 1 atm gives you the highest U. I just focus at 400 degrees Celsius, 95, 75, then this one here will be 40. So what I can say is, as pressure decrease, so now I'm going to focus on pressure. As pressure decrease, this one is as pressure decrease. Okay, as this one is as pressure decrease, okay, the U decreases. How do I know? Because at 1 atm, the U is 95%. And when it drops to 0.5 atm and 0.2 atm, the U becomes 75% and 40% respectively. Okay, so you realize I mixed the whole idea of the graph description together with the data coding in this whole question itself. Okay, so be able to do this, you are expected to also be able to explain the graph itself like that. So there's a skill that you're picking up from this particular chapter of Ammonia, not just knowledge itself, but the skill of interpreting graph, especially the graphs in multiple lines. Okay, so yeah, actually that will be it already. So in summary of this chapter, you learn about the Haber process and you learn that it's a reversible reaction. Okay, you learn about the conditions for the Haber process. You learn about where the reactants come from, like nitrogen and the hydrogen. Okay, and lastly, you learn how to interpret the interpret the data from graph about industrial process. Okay, so that's all really for this chapter. If you want to do more questions and wrap up when school reopens, I'll give you the ammonia worksheet and assignment. That's one. Second one is you can look through all these worked example, okay, which is actually not bad. Plus, also you can look at your TYS on the chapter of ammonia. So these are sources of questions that you can refer to help yourself get a better grasp of this particular chapter. So very quick chapter, and we are done already. Okay, I'm gonna stop the recording now. Okay, those of you who got any questions, you can stay back and ask me. Okay, other than